recording. I don't want to forget that because we've got a formidable YouTube audience for whatever reason. Okay, let's see. So it's nice to see you guys. Welcome back to another lecture. Hopefully you've all turned in your homework. If not, then I guess we'll see you in Chris's office hours after class today. Speaking of which, if I'm hanging out in your office hours, something has gone wrong because I'm supposed to give a talk to a bunch of undergrads after class today. And so please shove me downstairs. That is everybody's goal at the end of today's lecture, is to tell me that I need to go to the Europe lecture hall or I'm going to be in trouble. But in any event, right, so in terms of announcements and stuff, your next homework is already posted. Chris and I had lengthy debates about what we should make the last problem in your homework, and then we decided we've abused you enough, so it's just a little shorter instead. So reserve a lot of time for your last homework. You know, there's a conservation law here. No, I don't. But in any event, this particular homework covers optimization. You are going to implement a particular technique. You know, you might notice that each of our homeworks is kind of drawn from a different subfield of computing. Is kind of our goal here. This one, you're going to implement an algorithm for graph embedding. So you're given a network, and your job is to like visualize it on the plane, right? So like you're given the lengths of, or in particular, like distances between a bunch of different things, and you're trying to find an embedding into, I guess, Rn, probably R2, because that way we can plot it just for purposes of homework. And in particular, there's an extremely non-convex model, which is very popular in this thing. It is stress majorization, or wait, what is it? Stress minimization by majorizing, so the A is majorizing a complex objective function or something. Yeah, it's you know, sometimes there are these acronyms that some idiot made in the 80s and we're stuck with forever, and this is one of them.
It's scaling by majorizing a complicated function.
Scaling by majorizing a complicated function.
Wait, how do you say that?
Smackov? I don't know, but it is it is one of these state-of-the-art tools for embedding graphs and distance matrices. So essentially, there are a lot of different ways that you could optimize this objective function. If you plot it in 1D, by the way, it looks something like this. If you had a graph with a single edge, the idea of being like, I want things to be 1 unit apart, so like kind of that's, so it's obviously very non-convex. So in any event, you could do this with gradient descent. I believe if you want some extra credit, you can implement that algorithm, and you'll see that it's slow. Or you can use the smack off algorithm, which makes me very uncomfortable to say. And essentially what this does is it uses another optimization technique, which we haven't covered in class, so it's going to be a little bit of an extension of our lectures. In particular, there's a technique called majorization. Figured I'd talk you through this for a minute before doing the lecture content. The idea of majorization is that you take an objective function, maybe it's convex, maybe it's not, and like you have your current iterate, and then what you do is you kind of like come up with an upper bound for your objective function. So it's not necessarily a Taylor series anymore, but it is like an upper bound, and then you optimize that, and you iterate. So it kind of looks like Newton's method. And one thing that you can convince yourself is if you choose that upper bound very carefully, well, obviously minimizing the upper bound is going to reduce your objective value, but it won't take it to its global minimum. So in the homework, you're going to show that the objective decreases in every step. You are not going to show that this algorithm actually converges. If you'd like a good mathematical challenge, actually showing that the sequence of graph embeddings you get converges to a fixed point is actually not so obvious. But anyway, that's what your homework will be about. So now we've had one, let's see, we started with, what was the first homework? What coding did we have? Oh, right, logistic regression. Yeah, so we started with like an interesting logistic regression problem, then we did some 3D deformation stuff, then we did kernel learning. Next we're doing graph embedding, and the final one will be kind of in the differential equation universe, so maybe we'll borrow some problems from physics. So anyway, any questions? Just wanted to get you excited for your next homework. I know you guys all eagerly check your inboxes waiting for the homework to come in. Okay, so in any event, in this lecture, I forgot. I was giving us you guys a preview of our next lectures at the end of our previous one, and I forgot about this one. So if you take my list of what's coming next in this class, you can shift it by one lecture and insert today's. You could take entire courses on convex and non-convex optimization, and many of them exist here at MIT. This is definitely a survey course, so we only get to kind of give you the idea and the practical kind of aspects of some of these techniques. And obviously, there's sort of one final piece of the puzzle that's missing before we go into really specialized algorithms for kind of the generic version of optimization, which is how do we incorporate constraints, right? So in general, of course, the kinds of problems that we want to solve here are to minimize over maybe some unknown x, a function f of x. So far, this is what we've covered, right? But now we're going to say st, which is apparently subject to, and we're going to add two constraints. G of x equals 0, and h of x is greater than or equal to 0, right? So for instance, minimize cost to my company using all of the material that I have and never exceeding 3 hours of work or whatever. You know, like it's not hard to take problems and write them in this form. So a few notes, by the way, just before we get started with this discussion. So again, here's our problem. This is, of course, a wildly generic problem. So for example, let's say, let's think about some special cases here. So like, how could I do unconstrained optimization? Well, I could take G equals H equals 0, right? And now I'm doing unconstrained optimization on F. Yeah? What are some other ones? How about root finding? Well, if you think about it, if I take F equals H equals 0, then if I found a feasible point for this problem, in other words, I just found any x that satisfies the constraints, well, I've necessarily optimized the function 0. So a solver for this problem also tells us how to do root finding, right? Finding a point in the feasible set, like, so in other words, finding a point where a function is positive is kind of similarly structured here. So hopefully, the reason that I want to write it like this is just so that you guys realize, like, let's say that I am a software salesman, and I come into your office in the data center or the math department, if you've got a sad, not nice office. And I tell you, I've got this fantastic piece of software. It just takes function pointers to f, g, and h. It gives me the minimizer. Like, should I trust that piece of software? Probably not, right? Because like it's solving like a wide host of different NPR difficult problems, right? But that said, there are a lot of generic strategies for optimization, and it's worth covering. At the very least, maybe they often do work with guarantees in restrictive cases, like convex problems. And even if your problem's not convex, if you have like a good initial guess, it can make it better, like that kind of thing. Does that make sense? Incidentally, let's say I wanted to maximize f of x. Notice that this problem, and then subject to the same constraints, notice that like if I replaced f with minus f, that's the same as minimization. So that's why we're just going to only think about minimizing today. One math trick that we probably won't need today, but it is worth knowing in case you read certain textbooks that are a little bit lazy. Sometimes you see that this constraint is left out. In other words, you just have inequality constraints. Why is that actually kind of okay? Axel. Yeah, so if I have g of x is greater than or equal to 0 and minus g of x is greater than or equal to 0, these two things together imply that g of x is equal to 0. Yeah? In practice, this is not a fantastic idea because the space between these inequality constraints is nil. So if you're like having some algorithms trying to like wobble around in the feasible set to find the optimum, it's going to have a lot of trouble. So this is often not a thing you want to do except in some very restrictive cases. But like if you're just proving theorems about optimization, it's perfectly fine. Yeah. Any questions so far about our setup here? Yeah, I think this is like give it conditioned on all the other stuff we've done in this class. At least the setup here is pretty straightforward. One thing to remember is that here everything is vector valued. G, H, and G and H are vector valued. F takes a vector as input and outputs as a scalar. So in other words, we can have more than one constraint. Okay. And as I mentioned, like these problems are really hard. They are simultaneously optimizing, finding routes, finding feasible points all at the same time. Like a tool that does this thing well is doing a lot of stuff all in one. Okay, now there's no shortage of applications for this stuff. The textbook walks through a few. I'll briefly mention them here. For example, one kind of fun thing that people want to do sometimes is render implicit surfaces. So for example, if you looked at computer graphics in like the 1980s, people would often model surfaces using this particular thing. You might have actually played with this, and like occasionally some 3D modeling tools, which are kind of fun to play with. They use something called blobbies, which it's interesting. It was proposed by 2 different research papers, I think in the early 90s, or metaballs. Have you guys ever seen these things? I almost wrote meatballs, but I'm hungry. But essentially, basically what you do is very simple. You design a function f of x to be like a weighted sum of minus like x minus some xi. So you like place a bunch of points xi, and you stick like little Gaussians at those points, and you add them together. And then you just look at the set of points where f of x is equal to 0, and you call this like a surface modeling tool. So you move around the xi's and maybe like the weights in front of these things. And if you think about it, it's kind of like combining spheres together into these weird blobby shapes. So like for instance, maybe I have 3 points, and then like I have these Gaussians that kind of drop off like that, and I add them all together, so I end up like modeling some surface that looks kind of like this. So if you look at, do you guys know the old TV show Alex Mack? Am I totally dated? Or how about that scene from Terminator where he like turns into a fluid? Right? Yeah, you know that one, but you know what I mean. Right, so all of these things, like if you look carefully at the surfaces, they're like very lumpy looking. And oftentimes they're modeled with tools like this. So it's like an implicit surface that is like a sum of a bunch of little Gaussian functions, because that's very easy for artists to control. So in any event, if you're looking for an optimization problem in this space, you know, it might be I have a problem in 3D. I want to find the closest point on this implicit surface. Obviously, I can do that by solving a problem like this. These days, by the way, even if you're not just excited about scenes from Terminator, if you look at the state-of-the-art machine learning tools for making 3D shapes, they are often the 0 level sets of a neural network applied to 3D. This is called a neural implicit. And so actually these problems get solved a lot inside of the neural network domain after you do your learning. So you like infer this function in 3D whose level set is your shape. There's an example of this in the textbook notes if you look. Another common application is non-negative least squares. So far we've done a lot of ax equals b in this class. One might say too much. But like let's say I'm doing linear regression and I know that there's a positive relationship between 2 variables. Like, I don't know. The more sunlight that I shine on a surface, the hotter it gets, right? I just don't know the rate at which it gets hotter. I could very much constrain the coefficient between those 2 things to be positive, right? Like, because I know something went wrong if it's negative. Sadly, if I do that, all of the solution tools we've talked about so far in this course are no longer relevant. So we need to repair that situation. Or there's lots of other ones. So for example, here's a fun one that's kind of drawn from problems that are close to research that I study. Let's say I'm in manufacturing, and I have some set of materials. So I've got like, I don't know, flour, sugar, and eggs. And I'm trying to make a bakery, right? So I've got, you know, some amount of each of these materials in stock. I've got some number of products I want to make. Each product makes a particular amount of product, but it also requires some amount of materials, right? So like cupcakes require, 2 cups of flour and 6 cups of eggs. Or something. I don't know. What goes in a cupcake? Probably the opposite ratio. And raisin bread requires yeast and flour, whatever, right? And then you could very easily ask a question, which is, I want to maximize my profit, but I can't use up any of my supplies, right? So if we translate that into mathematical language, it would look something like this. So here, right? Remember that. So we're going to say our variable here is xj, which is the amount of each product that I make. So now our profit is just the dot product between p and x, right? This is like the amount of dollars I make for each unit of x that I make times p. But here's the thing, I can't make a negative amount of product, for sure. And moreover, what is the second constraint saying? Can anybody kind of read that equation and give me an idea? Remember, Cij is the sort of amount per unit of j that I need of ingredient I. That's right. So it's saying that I cannot deplete my, or like I can deplete my supply of unit I, but I can't go over that amount, right? If I have 10 cups of flowers, I can't make a billion cupcakes. Or maybe I can, but they're really small cupcakes. Incidentally, the cupcake example isn't great because there's probably an additional constraint which is missing here. Yeah, that's right. That I probably don't want to make a quarter of a cupcake. Now, when I bake, that's probably not true. I just throw the rest in a little pan. But if you're a professional, that is the case. And sadly, the integer constraint makes these problems much, much harder. So we are not going to cover too many strategies for that. They are briefly mentioned in the textbook, in particular these cutting plane methods. But that's a lot of the scope of a one lecture discussion. But yeah, so anyway, hopefully it's pretty clear that, like, you know, this language here encapsulates so many problems. And like just a good life skill, and hopefully one that you guys are improving on in this course, because it's something I've tried to add to all of your homework, is to just get you in the habit of looking at a computational problem and writing it in this form, right? Like almost everything we've done in this course, we've found a way to kind of reduce it to something like this. And there's no shortage of other examples. So another good one is bundle adjustment if you're in computer vision. So here, let's say I take the same photograph of an object from two different angles, right? And moreover, I mark on these photographs, like, you know, the tip of my nose. So I take, you know, a photo of Paul from the left and a photo of Paul from the right. And now I ask the user to like click his nose and his eyes and his mouth or whatever. So I've got some set of points marked on both of them. And now if I take enough photos of Paul, we all have many of them, then eventually we want to be able to reconstruct his whole 3D structure, right? So in order to do that, we want to figure out where the camera was, right? And so one way to do that is to say, okay, what are my variables? Well, maybe my variables are the projection matrices of my camera, right? The things that take the space positions in 3D space into the position on the photograph. And now what I'd like is that if I take these points in 3D space, these yj's, and I project them onto each image, I should get the location that I got in each of the images, right? Notice that there are actually like kind of two sets of variables in this problem. One is the 3D positions of all the points, like where is Paul's nose? We know where it is in the photograph, but we don't know where it is in 3D. And the other set of variables are like the camera parameters. I put orthogonal here. Actually, in the textbook, I fixed this. It's not really orthogonal. It'll be like a, you know, given like the position of the camera and the direction it's pointing, there's a formula for the matrix that takes you into the image plane. I encourage you to take 64400 if you like learning about those kinds of things. This is called the bundle adjustment problem. There's a lot of software out there. Even today in machine learning world, we still use tools for this. So like, for instance, these NERFs that are all the rage, the ingredient you need for a vanilla NERF is actually a set of images and known camera locations. So a pre-processing step for that procedure, as it was originally proposed, is to call a tool that solves exactly this optimization problem. By the way, are these problems easy or hard? Just like numerically speaking. They're really hard. Yeah, I mean, it's shocking that we can do well. Like, if you think about it, you've got a product of two variables here. So already your objective is quartic, right? Because there's a square and they're multiplied by each other. And p is probably a complicated function with like cosines and sines in it, right? So these are hard problems to solve in practice. They're often kind of prone to local optima. This is a problem that's been studied forever. Cool. So hopefully I have impressed upon you all the importance of developing optimization tools. So we're going to cover a little bit of basic terminology. Then we're going to go through one really central theorem in this space. And then we're going to talk about some optimization algorithms for this. This might spill over into the next lecture a little bit, and that's okay. All right. So let's get started here. So first, some definitions. Feasible point. This is exactly what it sounds like. So the feasible set is the set of x that satisfy these two constraints here, right? So like, for instance, in our industrial problem, it would be like the set of different, you know, amounts of each thing that we could make that doesn't deplete our supply, right? So it's not necessarily optimal, but it's at least satisfying all the constraints. That makes sense? And then when we say that we're looking for a critical point, what we mean is that you are both feasible and a local optimum, meaning any perturbation which keeps you in the feasible set necessarily increases f. Okay. Now this definition is a little vague. We're going to fill in what it means differentially to increase stuff. And in particular, we're going to define optimality conditions for these kinds of problems. But does this vocabulary make sense? I think this is likely you guys have seen this elsewhere, but I'm happy to clarify. We're quiet today. Actually, that's not true. You guys aren't quiet. So we've already heard from Harry and Axel. That's great. Okay, so what do we do? So let's forget that we know algorithms for a minute and think back to calculus class. So let's say that the constraint h weren't here, and I presented you with one of these problems. What would be your reflex? Like, how would you go about studying and understanding this problem? Like, what is the calculus tool that's relevant to constrained optimization, which we've used many times in this course? Yes? Lagrange multipliers. That's right. So in particular, we kind of know how to study these problems using tools of calculus if only that h weren't there, right? Like in particular, what do we know? We can construct this thing we keep calling the Lagrangian, which is a function of x and this new object lambda that we call Lagrange multiplier. And then essentially what we show is that critical points of this thing with respect to x and lambda jointly correspond to optima of our original problem. Yeah? Sadly for us, I was annoying and I added this h here. Yeah? So does this Lagrange multiplier formula apply anymore? Sadly, no, at least not the way we've written it, right? And so our first goal for today, which might be our only goal for today, looking at the clock, because I'm already talking too much, is to establish what is the equivalent of Lagrange multipliers when we have inequality constraint, right? Because that's what's going to allow us to sort of understand how to formulate these algorithms, A, and B, actually, it also suggests, at least in the case of convex functions, some really clever algorithms that are really subtle for optimizing these things. You sort of end up searching for lambda instead of x. In fact, if you did one of the exam problems correctly, which I think was one of the harder ones, you saw an example of exactly that. This constrained least squares problem, right? You ended up searching for a dual variable. I hope. I haven't looked at your exams yet. Spoiler alert. Okay, so in any event, basically our task for the next 45 minutes or so is to figure out, like, okay, what happens if we stick this stupid h in here, right? Any ideas? What should I do? Just out of curiosity, has any of you guys seen this story before? This is just a mathematical picture, so one or two. Okay. And as a warning, I cooked up my own proofs for this stuff, which means it's probably wrong. But they're very intuitive, so that's good. Okay, right, so essentially, as a sort of preview of what we're aiming for, there's a set of conditions similar to Lagrange multipliers for inequality constraint problems. These are called the KKT conditions. It's actually kind of an interesting story academically. Do you guys know how this goes? So it's the Karush-Kuhn-Tucker conditions. And for the first, 30, 40 years of their existence, they were just the KT conditions for Kuhn and Tucker. And then, who were like famous, like pretty well-known numerical analyst type people that were studying this stuff. By the way, these results are fairly modern. It's like the last maybe 70, 80 years, like relative to Lagrange multipliers, which are much earlier. Karush was a master's student, which is a great, great story for our MN students here at MIT. And somebody found in, I think, like an appendix of his master's thesis, exactly the KKT conditions. So he actually gets the first K, which is great. But anyway, it's a fun Wikipedia page to read. So essentially, what we're going to try and do is intuit how Karush, and then a couple years later, Kuhn and Tucker apparently kind of came across these conditions. Because I think what is common is to see them in a math class where they're just presented to you as like gospel, but like they're actually very natural. And if you kind of go through the steps the right way, it's kind of reasonable why they might come about. So that's going to be our goal. So first, I think the first thing to think about when we talk about inequality constraints, we're going to introduce one more little piece of terminology here, which I think is a very natural one, which is the following. This is the difference between an active and an inactive constraint. So here, so when I was drawing all these pictures, like I really didn't want convex problems, so you end up with like a lot of like weird bean-shaped things. I'm sorry. But in any event, here's how to read this. So like the gray region is going to be the inequality constrained region. Here maybe we don't have equality constraints because those are going to be kind of easier to deal with. And then the black lines here are the level sets of the objective function. Does that make sense? So like for example, on the picture on the right, notice that like the minimum of the objective, like the innermost black bean, is contained within the feasible set, right? On the left-hand side, what happens? The minimum point of f, right, this point here, is not within the feasible set. So when I add the constraint, I can no longer call that the optimal point. It has to move. Does that make sense? So notice that there's basically two cases that can happen here, right? When I optimize, and sadly, this is like an a posteriori kind of argument because I had to find x star, right? But like, essentially, when I look at x star, one of two things is true. Either x star is within the feasible set, right? In which case, what would happen if I removed that constraint? Nothing, it would stay optimal, right? Or x star is right on the boundary of the feasible set, right? And probably in that case, what's happening is that like, if I let go of that constraint, x star will want to move to a lower value. Does that make sense? And so essentially the only difference between KKT conditions and Lagrange multiplier is this picture right here. And because think about what's going on here. If you think about it, there's sort of two cases. If I'm in the interior of the constraint set, I could have just removed x star, right? So in that case, like I should just remove the constraint and throw it away from my Lagrange multiplier condition. And if my constraint were active, well then I could have made an equality constraint, and notice like because I'm on the boundary of this set, I would have gotten the same point. Does that make sense? And so like, if you think about it, what does that mean? That means that like Lagrange multipliers kind of still apply, but only if I knew which constraints were active. You guys get that? Here's what's the problem with that, like from a practical perspective? Yeah, you gotta know which constraints are active. Now there's actually a completely reasonable strategy, which some algorithms, like the simplex algorithm for linear programming, more or less do, which is the following. So let's say that I have n inequality constraints. So there's 2 to the n options for like all the different ways that they could be active and inactive, right? So one thing that I could do would be generate those 2 to the n vectors. For each one of them, solve the Lagrange multiplier problem, and then just choose the one that like where all the constraints are satisfied and has the lowest objective, right? That's perfectly fine. Is that algorithm particularly efficient? No, right? So what the simplex algorithm does is it walks through those kind of binary vectors in a very careful way because it knows a little more about the problem. Right, so in any event, sadly for us, simplex algorithm only applies to linear stuff, so we're not going to touch that here. And instead, all we know is the following. So x star here is going to be our notation for the optimal x for our optimization problem. And essentially, x star has one of 2 conditions. Either hi, so that's going to be the ith constraint. By the way, I'm going to use I to index inequality constraints. And is that right, or did I already get it wrong? Oh no. On the board, I'm going to use j's to index the h's and i's to do the equality constraint, but I've already made a mistake. So forget that last sentence. The constraint is active if actually the constraint is equal to 0, and it's inactive if the constraint is greater than 0 at that optimal point. Does that make sense how that translates to the picture? Cool. And again, the only problem here is we don't know the optimal point. So if only we did, what would we do? We'd just throw away all these constraints, keep these guys, but convert them to equality things, and now we're back to like Lagrange multiplier. Okay. So that's what we kind of want to do in theory. And if you think about, like essentially the way that I like to present KKT conditions is that this is a mathematical sleight of hand that takes that logic and translates into symbols, and then what usually happens, people completely forget that logic. But that's really all that's going on. Is essentially we'd like to remove all the inactive constraints and make the active ones equality constraints, but we don't know how to do that. So here's going to be the trick. This is a really sneaky trick. I just love this. And it's like one of these ones where you look at the first time and you feel like, oh God, like that's not valid. And then like you step back like 10 feet and actually it's perfectly fine, but it just feels uncomfortable because it's sort of the way that you get there is a little illogical. So we're going to, like, you have to figure out which things that we're doing are definitions and which things that we're doing are actually, you know, sort of theoretical byproducts. So I want you to be skeptical as I write things on the board, largely because I make a lot of mistakes. Okay. So for our constrained optimization problem, which conveniently, for once, I haven't erased, it's sitting on the top board here. I can construct a Lagrangian very easily. Right? So in particular, I'm going to introduce Lagrange multipliers. We'll call them lambda for the constraints g and mu for the constraints h. Okay? When I say I can construct Lagrange multipliers, that already sounds fishy because we know that Lagrange multipliers don't apply. But we can construct a function that looks like Lagrange multipliers, and we can see what we can say about it. Okay? So in particular, here's what I'm going to do. I'm going to construct a Lagrangian, lambda, and it's going to be x. By the way, I kind of like this notation where like x is the primal variable, and then I put a semicolon, and then lambda mu, just to separate like primal and dual here. It doesn't really matter. That's the way I like it. And I wrote the book, so I get to do that. Okay, so what is this thing going to be? I'm going to define it to be f of x minus, I want to be really careful to make sure I get the sign right. By the way, every textbook disagrees on sign because there's like a lot of different conventions you could use here. So since I borrowed some of this from other books, there's likely mistakes. But we're going to see how far we get. So this is the Lagrangian, right? Like, so for example, if this were an equality constrained problem, this would be the thing whose critical points I want to take. Do you see that? Like I've separated what I usually call lambda into two vectors, lambda and mu, but that's like not critical. That's just notation, right? So let's do something that's mathematically completely invalid. So suppose that we forgot that some of our conditions were not satisfied. So, or in other words, suppose we forgot that some of our conditions were inactive, rather, right? In that case, what would be the critical condition with respect to just x, not a mu or a lambda here? It would be the following. It'd just be 0. I'm going to do a weird thing, which is question mark equals the gradient with respect to x of lambda, right? Because that's the condition you would get if there were all equality constraints. They're not, but you see why I keep saying the sentence. I want to make sure it's clear. This is not there's no implies arrow here. Okay, but just for completeness, what is this thing? So it would be grad f at x minus, I'm going to, by the way, I don't usually do this in this class. We like to use vectorized notation. But like because we're about to take gradients of each of the g's independently, I'm going to write this as a sum. Okay? So in particular, this is going to be minus sum over I, lambda I, g I, grad g I of x minus sum over j, mu j, grad h j of x. And again, I'm going to try and be careful to use i's to index the equality constraints and j's to index the inequality ones. So there's a question mark there because it's certainly not true that it's a critical point. But I claim we can kind of like repair this a little bit. And here's going to be our little hack. This is just between me and you. Let's say that I say, let's consider the points x, or really x star here, right? So that's the critical point. Like, let's say that they satisfy two things simultaneously. One is this condition, and the second, we're going to just throw in there for yucks another condition. Sometimes this is called complementary slackness if you've taken a linear programming class. And it does the following. It says mu j times hj of x, I guess star, is equal to 0. Now, this looks very profound. It's like a product and like things are 1 over other things, whatever. But actually, this is like a totally boring expression. What it's saying is that one of these two numbers is 0. Okay? So suppose I consider a point x star that satisfies both of these conditions at once. So it's x star, and also we need to know mu and lambda, right? So now let's look over every index j, okay? So one of two things is true. Possibly both, but at least one of two things. First of all, let's say that my constraint is active, right? Then what does this expression do to mu? Actually, nothing, right? Because if my constraint is active, what is hj? 0, right? That's the definition of being active. So in that case, this thing is satisfied, and mu j can be free. Okay? So in particular, notice when my constraint is active, what's the thing that's constraining mu j? Well, it's actually the Lagrange multiplier expression, which is fine because that's exactly what we want to happen, right? Because when it's active, now Lagrange multipliers make sense, right? Now let's say the constraint is inactive. What do we know about h in that case? What's the definition of inactive? Positive, right? In other words, like that constraint doesn't matter. What do we know about mu when the constraint is inactive? Well, these two things multiplied together give me 0. I just said h is positive. So mu 0. So one of two things is true. Either I zeroed out that term in the Lagrange multiplier because it was inactive, or the constraint was active, and then I had the Lagrange multiplier condition. Isn't that sneaky? This is such a sneaky trick. Essentially, the way to think about it is like sort of a posteriori, we can erase that question mark here, right? But it's not obvious, like writing down this expression, like without this thing, it would not be true. So anyway, I feel like when we see complementary slackness, people kind of like view it as a very profound thing, but really it's just saying like, I gotta zero out one of these guys. That make sense so far? Okay, so currently we have a lot of necessary conditions, but not sufficient ones. So in other words, like if x star is a critical point and we can find lambda and mu so that this is true, we haven't shown that like this characterizes critical point. Yes?
When either h is 0 and mu is non-zero or the other way around,
Mm-hmm.
is there any kind of interpretation of the other thing doesn't have to be 0? Does that have any kind of like...
Yeah, Lagrange multipliers like can be 0 when you satisfy the constraint. That's actually perfectly fine. Yeah, that's basically what it's saying then. If you think about it, what that ends up looking like is kind of like you're satisfying the constraint to like some higher order, is kind of what's going on. But yeah, it's a good question. Any others? Okay, so in fact, these are 2 of the KKT conditions, but we can actually derive some more. These are just like all the cool, fun things that are true about KKT conditions. By the way, there's a few other things we know about x star. We know that g of x star is equal to 0, and we know that h of x star is greater than or equal to 0, right? So there. Okay. However, there's actually still one corner case that we have not yet covered. And this is the one that makes me very uncomfortable to prove things about, so we're going to see if we can do it together. Incidentally, the first edition of the book, for those of you watching on YouTube, is completely wrong here, but we fixed it. And I had 2 of my postdocs check, and neither one of them found a hole, so Harry will, but then he gets to feel superior to 2 postdocs. Okay, so here's going to be the schematic. Make sure I didn't forget anything. Nope. So here's a weird thing that can happen. It's just the following, which is like maybe we're at a critical point of our function, but we can still like, so we're at a critical point of our optimization problem, but we can actually kind of move inward to increase our objective function. So in other words, we like so far these KKT conditions have not like differentially, what's the word that I'm looking for? They haven't distinguished between h of x greater than or equal to 0 and h of x less than or equal to 0 in the calculus part of this problem. And that feels like a problem. And so that's the one missing piece. Okay? And this is going to lead us to another condition that's usually called dual feasibility. By the way, we use this word dual a lot, and I'm going to try and justify that after we derive these conditions. Okay. So here's going to be the trick, and this is one that makes me very uncomfortable. So we're going to see if we manage to get it right. You can see in my notes, I drew 4 different diagrams and then scribbled on top of each of them until I converged on one that I think is actually the one that we want. Okay. So we're going to do it in a special case of 2 constraints, and then we'll talk about how we extend it to more than 2 constraints, which is basically the same, it's just more writing. Okay? So, in order for this picture, as I figured out empirically yesterday at my office, for this picture to not end up horrendous, we want to have 2 constraints that meet at an angle that is bigger than 90 degrees. This is purely for pedagogical reasons, and all the math is perfectly fine when the constraints are pointy, but the diagram gets really ugly, okay? So, in particular, here's going to be our constraint set, like that. So here is going to be like this curve you can think of as like h1 of x is equal to 0, this curve is going to be like h2 of x equal to 0. Okay? And we're going to think of this as like our feasible set down here. Everybody understand the picture so far? Cool. All right. So let's say that I'm at this critical point. So I've actually got two active constraints. Yes? No. Maybe we just did, yeah, why are they straight lines? Because I zoomed in so close to this point, everything looks like a straight line. That's a posteriori. There. Happy? Maybe like a little. Okay. I would not want to try and optimize this function, but I digress. Okay, so I found a critical point, and it's right at the intersection of these two constraints. So we have two active constraints, possibly some inactive ones. But notice for the inactive ones, it kind of doesn't matter. It's just the active ones we have to worry about. So there's sort of three different vectors that are at play here. Do you see that? In particular, there's the gradient of f, the gradient of h1, and the gradient of h2. Okay? So here are some things that can happen. Let's say that my constraint is active, but like really f is optimized out here somewhere, so like really the constraint is doing some work. Then like f is going to have a non-zero gradient. Like there are directions at f points that want to move you in or out of the feasible set, right? So let's say that the gradient of f is like this. Is this a valid optimal point? Remember, the gradient points in the direction of steepest ascent. Yeah? So if I want to decrease f, I would move in this direction. Am I at a local optimum? No, right? Because I can move into the feasible set, and I can increase the value of f. Yeah? I'm at a point where, like, I figured out the right, like which constraints are active and which ones are not, but like the gradient of f points the wrong way. Yeah? Okay. Let's say I flip this picture backward. Now, this is the gradient of f. Notice that now, like, this makes sense, right? Like, these critical points are, or rather, these constraints are the thing that are preventing you from moving farther. Does that make sense so far? Okay. So now let's think about, in order to work out the dual feasibility condition and like draw a good pictorial representation of it, it took me a few tries. And in particular, here's the picture I came up with. So let's say that the gradient of f, so again, if the gradient points inward, then like we know that like there's nothing we can do, right? However, let's say that the gradient points like kind of close to parallel to this edge here, like that, right? So like at least to first order, if I draw like a vector that's like a line that's perpendicular to that gradient of f, notice if I move anywhere in this half plane, I can like decrease f. Does that make sense to everybody? So is this a critical point? No. Why is that? Well, I can't move into the feasible set, right? But I can move along this edge and decrease the value of f. So in other words, what went wrong in this case was kind of like what constraint is active, right? Like I didn't really want this constraint to be active. If I made it inactive and moved this way, I'd be happier. Does that picture make sense? Like the reason I'm drawing all this stuff is that I think it's very easy to kind of say like, oh, as long as like my gradient vector points inside of this little cone here, then like maybe I'm happy. But that's actually not true. And this is the reason why. Now you can see why I wanted to draw this angle bigger than 90 degrees. Okay. By the way, when you're not on a blackboard and you're in higher dimension, then the 90 degrees doesn't matter as much. Okay. So does everybody kind of see what we're aiming at, like pictorially? Okay. So now our goal is to translate this picture into math. Okay. And we're going to do it with two constraints. The notes do it with n constraints. It's exactly the same math. It's just that the notation is uglier. And I'm lazy. Okay. And this is a decision I made 20 seconds ago. Okay, so let's clean up our picture. And by clean up, I mean make ugly erasure. Okay. So here's our point x star, like that, right? And what we're going to consider is like a small perturbation delta to x star. just generically. Delta is not the gradient of anything. It's just like a possible direction I could wiggle x, right? And if we're at a critical point, what do we want? We want that any direction delta either increases f or moves me out of the feasible set. You see that? So again, if I map x star to x star plus delta, either, let's call this, I don't know, y. Y is infeasible, or f of y is greater than or equal to f of x. Right? That's what it means to be locally optimal for like small deltas. Cool? I'm trying to do this in very small steps because I feel like these conditions are easy to get wrong. Okay. But now I think you guys have figured out that like when proofs get really slow, it's because of my own discomfort rather than anything else. Okay, so in particular, to first order, here's a bunch of true facts. So remember that we want h to be greater than or equal to 0. So if I take a gradient of constraint j and dot it with delta, remember that constraint j we're going to assume is active here, right? So if I take a delta and it is positively correlated with the gradient, right? That means that delta moves. Well, if you think about it, what does that mean? That means that delta increases h, right? Which means it moves into feasible set of h, j. Cool? Okay. Similarly, if I have grad f and I dot product with delta and I get something positive, that means that delta increases f. Right? You can kind of see what we're doing. We've got like all these different half planes that we've cut out, and now we want to show that their intersection is empty. Everybody with me so far? Any questions about our story? Okay. So, what do we want? We want, I'm going to write it in words first, and we're going to translate it in math, because that's what I did in my notes, and it helped me. We're going to say that all vectors moving into the feasible set so if you move into the feasible set, what must happen to our value of f? Because I'm at a critical point. It has to get bigger, right? Now you can see how it's easy to get this argument backward. Okay. So here's what we're going to do. Yeah. Oh no, I erased my Lagrangian. I'm sorry. So actually, let's continue this argument a little bit. So suppose the constraint k is active. Okay? We're going to derive a condition that tries to kind of mimic this story here. Okay? Well, in that case, we're going to define a really weird object. This is this thing we're going to call delta k. Right? This is going to be kind of like, like a little probe vector that we're then going to apply this fact to and derive a really nice little condition from. Right? And unfortunately, it's a little bit ugly. Because like what we'd like to do is look at the set of all directions that increase h, but we still have to account for all the other constraints. Because remember when I drew that vector, it had to be in this little sliver here in order for my story to work. So here's how I'm going to do it. I'm going to say delta k is equal to the gradient of hk at x star. But I'm going to subtract off of that the projection onto the span of gradient h1 to gradient hk minus 1, gradient hk, gradient, whatever the last one is, hp, like that. of the same thing. By the way, I guess here I'm not including G, but you could also include all the G i's in there. So this seems like a weird vector, but let's draw a picture of what it is in this thing, okay? So first of all, the gradient of H1, we know points, oops, did I already get it wrong? I did. Yeah, sorry. The gradient of H1 has to point into the feasible set, right? That's what I got wrong. Remember, the gradient is 90 degrees to the level set. So the gradient of H1 is that. And there's a 90-degree angle there. Okay? What is the gradient of H2? Well, similarly, it's kind of like this vector here. Okay? So when I say delta 1, what do? I take the gradient of H1, and I subtract off its projection onto H2. So in other words, this guy is going to be like delta 1. Okay? So if you're keeping track in our picture of like what our construction is. Do you see how this ugly expression translates to that picture? So if you think about it, what it's doing is it's kind of like taking the part of the normal to our set and then just projecting out all the directions that would move into the feasible set of the other guys. And why do I do that? Well, take a look. Actually, I can displace that vector. And remember that it is now orthogonal to gradient of H2, right? That's why I constructed this thing. So here is delta 1. Sneaky, huh? Like basically this delta, at least at first order, points along the other constraint. Does that make sense? So remember that the case that we were worried about before where I could kind of like slide along an edge and increase the function? So hopefully now you can see why I made this weird construction. Essentially, I managed to choose a direction that moves into the feasible set of this guy and keeps the other guys satisfying their equality constraint. Any questions about that picture? I know these are tough sentences to parse, and when you're really on your laptop during my lecture, you miss some of the details. I get to pick up my grads too. Okay, so right, so that's what we've done. I basically said I'm going to slide along the edge away from constraint 1. That's the point. Well, all of these conditions we wrote down here apply, right? So in particular, here's going to be our little argument. So we're going to make a small concession here, and this is why our argument is an argument and not a proof. Notice that delta k dot product with the gradient of hk at x star, can it be negative? The answer is actually no, right? Because I started with hk and I subtracted out its projection onto a subspace, right? So like it would be really weird if it somehow flipped backward in that process. So in fact, what you can say is that this thing is greater than or equal to 0. Okay? Does that make sense? Like even pictorially, you can see that that's the case. It's moving away from H1. Yeah. And the reason for this again is that like this is just generically true. I took like a plane and a vector which may or may not be in that plane. I took its projection onto that plane and I subtracted it off, so I replaced it with that guy. So sort of necessarily this guy and this one they can never like point opposite each other. Okay? Here's gonna be our concession. Typically, if our constraints are not redundant, when your constraints are redundant, so in other words you have two h's that kind of join tangentially at a point, then this is violated. But ignoring that case, what we know is that this is actually a strict inequality. In other words, there's like some part of that subspace that's not covered by the other guy. Okay? Well, luckily for us, what do we know? Well, in that case, we better have, so this thing is greater than or equal to 0. What can we say about delta k dot grad f at x star? Well, you think about it. So I just showed that I stay in the feasible set, right? So this thing is at least greater than or equal to 0. Yeah? This is great. Now we know two things at once about delta k. That's why we made this clever choice of delta k. Generally, this is my construction. So if you're looking for a hole in my proof, that's where to find it. OK, so now remember that we have our Lagrange multiplier condition, right? We know that the following, that 0 is equal to grad, grad f at x star minus some lambda I gi grad gi x star minus the sum mu I grad gi x star, like that. Okay? So in particular, let's do the following. We're going to take the dot product of this expression with delta k. Okay? Does that make sense? I mean, certainly you could do that. Okay, so let's move. We're going to keep f on this side. We're going to move everything else to the other side. So we get delta k dot product grad f at x star is equal to delta k dot product with the sum lambda I grad grad gi x star plus the sum mu j grad g j x star. Cool? So all I did was take this expression, dot product with delta. Can I simplify this? So remember how we constructed delta. It is some vector minus projection onto a plane. And the plane happens to be spanned by all of these vectors. Oops, one of these should be, oh no, I wrote 2 G's and nobody caught me. This should be H, sorry. But in any event, what did I do? I took the span of all of these vectors except for one, and I took grad HK and I subtracted off that span. So what do we know? What is the picture here? So I've got, again, this plane, which is the span of all this stuff. I've got some vector that points outside of it. I took in its projection, so that's like this guy, and I subtracted it off. Notice, oops, I drew that little 90-degree sign there. So every term in this sum is equal to 0 with the exception of 1, which is mu k delta k dot grad hk at x star. And now we're like almost done, I promise. This is so sneaky. I love this little argument. A few of you look confused. Yes, Harry. See, there's a G in my projection. Yeah. We added that after the fact because I forgot. This is, I think, why people typically throw away the equality constraints when they derive this stuff. Otherwise, this expression, as you can see, takes the entire board. Yeah. Okay, but in any event, hopefully you guys can all see that basically this is exactly just this fact from linear algebra. If I subtract off a projection, then my dot product is 0. Well, this is really nice, right? So delta dot f is equal to mu times delta grad h. So to put differently, notice that this is greater than 0, so I can safely divide, right? So in particular, mu k is equal to delta dot grad f at x star divided by delta, oops, there's a k dot grad hk at x star. We just argued that both of these numbers, this one's positive and this one's greater than or equal to 0, or the other way around, sorry. So this whole thing is greater than or equal to 0. Ta-da! So what did we just show? We showed that mu k is greater than or equal to 0. So we did a really lengthy argument to show a one-line formula. So anyway, when you're looking at this funny condition that mu k is greater than or equal to 0, they call this the dual feasibility constraint. The way to think about it is as follows, that like if I'm at a valid critical point, I don't want to have this case where I could slide kind of away from my active constraint along the edges of the other ones and increase my objective function. That's really what's going on here. Any questions?
It has some interpretation too of like it's how much it's like how much D it lacks out or something.
Yeah, that's absolutely right. Oh, that's fantastic. So have you ever taken an economics class and seen this formula before? Yeah. Oh, okay, cool. So I've triggered one of our students. Great. A trivia question. Does anybody know what economists call mu k? Shadow prices, which is like a very shady sounding name for a dual variable. Why do they call them shadow prices? It's like roughly the amount of money that you pay to enforce your constraint, right? Yeah. So notice from that perspective, it kind of makes sense, right? You don't want that to be negative because then like the problem is paying you to enforce the constraint. You might as well have relaxed it. And indeed, that carries through. If you do sensitivity analysis on these problems, you'll see that like the rate of change of the objective value and so on like has to do with the mu. Yeah. This is easy for linear programming and annoying for other things. Yeah. Any other questions? That's a fantastic point. By the way, we're going to cover a second motivation. I'm thinking because we're low on time anyway, I'll give you a second motivation for KKT conditions rather than going through constraint optimization algorithm. And then our next lecture, we can do that because the homework, I don't think, really depends on this stuff. Cool. So at the end of the day, let's summarize what we've done so far. So I think the easy part of the Lagrange multiplier, or sorry, the KKT conditions are like everything except for the very last one, right? So X is feasible. It satisfies the Lagrange multiplier condition so long as mu times H is equal to 0. And basically, that's just a sneaky mathematician way of zeroing out terms that shouldn't be there, right? That's all that is. And then, you know, that hasn't distinguished between, you know, this thing being positive and negative. Like, can I move along an edge and kind of still increase or decrease my objective? So using this little argument, we derived this constraint, which even though our argument was ugly, the constraint itself is pretty clean, right? It's just that mu is positive. That makes sense? Okay, so that leads us to the KKT conditions, which say that essentially, if you're a critical point of your problem, there exist mu and nu that satisfy all four of these things. They have names. It's stationarity, which makes sense because it's borrowed from calculus. Primal feasibility, because remember, feasibility just means it satisfies all the constraints. Dual feasibility, we'll see why that is in like 2 minutes. And then complementary slackness, which is a fancy phrase for like, you know, either mu is non-zero or H, but not both. By the way, the complementary slackness phrase makes sense if you view it in light of that plus the dual feasibility condition, right? Because you see what it's sort of saying? It's like there are these two inequalities that can happen, right? Like either H can be positive or mu can be positive. And the idea is that like it's kind of sticky, right? Like if H moves positive, then mu has to stick to 0. And so that's where that phrase kind of comes from. Does that make sense? Yes?
Why primal?
Great question. What? So we see these weird words, primal and dual, and so far it looks like primal and Lagrange multiplier. And indeed, in this theory, that's absolutely true. Now let me give you a completely different way to derive the same formulas. This one is going to be more hand-wavy because in order to do it, you need a little bit of game theory. But I think you can do it modulo one mathematical sleight of hand, which I will carefully point out so our math student doesn't get upset at me. OK, so here's how we can do it. So we're going to go back to our Lagrangian one more time. So again, I accidentally erased our problem, so let's put it back. So it's g is equal to 0 and h is greater than or equal to 0. Yeah, so it's minimize f of x subject to g of x equals 0 and h of x greater than or equal to 0. OK? I'm going to write a really weird optimization problem down. I love this because, by the way, it leads to a shortcut to doing calculations that are really ugly in linear programming class. So don't tell your OR professor that I'm giving you this trick, which is as follows. I'm going to write down a problem that feels like it doesn't make any sense. And it's the following. This is actually the game theoretical way to get to Lagrange multipliers. Let's say that I minimize with respect to x. And now I'm going to do something that, like, the mathematical notation is a little fishy, but intuitively is actually kind of OK. I'm going to be careful to put parentheses in all kinds of places, because in game theory that matters. Like, who plays first in your game kind of is important. We're going to do the following. We're going to take the max over real valued lambdas and mu's, which are greater than or equal to 0. You can see that there's already some resemblance to our KKT condition. And what do you think I'm going to put here? I'm going to put our Lagrangian. I'm going to say f of x plus lambda dot, minus, sorry, wrong textbook, minus lambda dot g of x minus mu dot h of x, like that. This is a weird problem. This is on what we'll call the extended real numbers. Which is this funny thing. It's like the union, I guess I should write it, I don't know, the union of the real numbers and then plus or minus infinity. Okay? So here's the way to read this problem because it's a little bit tricky. The objective value for x is itself the solution of an optimization problem for lambda and mu. Does that make sense? So if I want to know the cost of x, I have to solve some other problem for lambda and mu. This like is a perfectly reasonable thing to do. I mean, think about like, I don't know, I'm doing my bakery and now I want to know like whether I should order more flour or not, right? So I want to increase my profit. So what do? I say, well, you know, the objective here is maybe to optimize the amount of flour that I buy, and now inside of here I have to solve that little linear program that I had before, right? I made that up on the spot, but I think it works. In any event, let's think about our objective function for a second. So we can call this inner thing. Let's give it a name. What do we want to give a name for this giant function just of x? I'm running out of letters. Give me a letter. Q. Thank you. Q of x. Okay? So we have two cases. Let's say that x is feasible. Okay? What is the optimal value? Like, what is q of x in that case? So first of all, think about it. So if x is feasible, what is g of x? 0. So then what does this thing do to the inner objective value? Nothing. Moreover, if x is feasible, h of x is positive, right? Mu has to be positive. Notice there's a minus here. So what is the optimal mu? 0. So both of these things contribute nothing, and we have q of x equals f of x. So that's kind of sneaky. Now, let's do case 2. X is infeasible. I love this trick. I do this trick like 3 times a week because it shows up in our research all the time. What is q of x? So first of all, let's say it's infeasible because I don't satisfy one of the equality constraints. So like, let's say that like g of x is equal to 3. What is the maximum value here? Infinity, right? Because I can choose any lambda that I want. I'm just going to take that 3 and multiply it by a ginormous number, right? Or I guess a ginormous negative number because there's a minus here. Similarly, let's say that it's infeasible because h is negative. Well, now this minus and this minus cancel, and I can take it to infinity again by just choosing a ginormous mu. So in both cases, when x is infeasible, we have q of x is equal to infinity. So what should the outer optimization problem do if it wants to minimize with respect to x? It had better choose a feasible x, right? So essentially, like what we've done is we just took our constrained problem, and we made it into an unconstrained problem on the extended real numbers by constructing an objective function, which is infinity any time that you're not feasible. This is dumb. It's discontinuous, but I can do it. Does that make sense? OK. So here's the kind of interesting perspective from game theory. You kind of view this as like a game. Like there's one guy that's trying to minimize this thing with respect to x. There's another guy that's trying to maximize this thing with respect to lambda and mu. And now we have essentially all of the different KKT conditions kind of fall out of this, except maybe complementary slackness, but you can convince yourself of that. Because if you think about it, like what's going on here? So first of all, the primal feasibility is because we know that we can get an optimal objective value that's not infinity, right? Dual feasibility is by construction. We just defined mu to be a positive thing, yeah? And then essentially we can get the optimality condition here. So yeah, so what are we missing here? Stationarity we can get by the fact that you're optimal with respect to x, lambda, and mu, all simultaneously. The only thing you're left with is complementary slackness. And you can get that because otherwise things would blow up to infinity. Yeah. This is a really slick way to derive these things. Now, if you take a linear programming class, I mean, this is like the world's longest answer to your question like 20 minutes ago, which is why do we call these dual problems or dual variables? So this is what some people call the primal problem. Now, here's where, watch out guys, this is where the bad math is going to happen. Under certain conditions, I can take the min and I can swap it with the max. I can do the following. We're going to do the opposite game. Just think of like an equilibrium perspective. So now we're going to do the max over lambda and mu greater than equal to 0 of the min over x, f of x minus the same thing as before. Minus mu dot h of x. This problem, thought of as a problem for lambda and mu, this is called the dual problem. And under certain conditions, these two things give me the same optimal objective value. So a very famous set of conditions for this are called Slater conditions. We will not derive these in this class, guaranteed. And essentially, they're extremely strong. They say like if your problem is convex and your constraints have an inside, so like there's a strictly feasible point, then these two things agree. It's a really useful constraint in practice. Yes?
Convex and it has a feasible.
Like a strictly feasible point. Yeah.
Or like that's just,
Convex things are not, well, they can be, except like they jump off to infinity. Yeah. So that's the other story. And notice it's just like another way to get to the KKT conditions. It's a perfectly valid way to do it. If you want to do it carefully, you have to kind of just, like you need some more conditions on F and G and H. But I thought for fun, we've got 5 minutes left, and I'm obviously not going to get to our algorithms. So maybe instead, let's do a quick example of that and see why this kind of theory is useful. In particular, I think in linear programming class, you spend about 5 lectures deriving what we call the dual of a linear program, and I claim we can do it in about 2 minutes. So here's what I mean. So the optimal cost problem that we had a few minutes ago is an example of a class of problems where f, g, and h are all linear functions. You can take entire courses here at MIT on just how to pose and solve those particular problems. Network flow falls into that category, and many other classical algorithm things. Harry is cringing because everybody hates. You don't hate these. These are. My expertise is network flow, so that's my PhD is like Hungarian algorithm. Okay, so right, I'm going to follow my notes to make sure that I get it right. Okay, so here's a really fun game, which is called linear programming. So remember, our objective and our constraints are linear. So in particular, let's do the following. Let's do minimize b transpose x, subject to the constraint a x is greater than or equal to c. Notice we're going to not have equality constraints for that trick that we showed before. We can make it into 2 inequality constraints. So what is the Lagrangian of this thing? In fact, let's just go ahead and write the minimax problem because we got it here. Right? So this is going to be min over x max over lambda greater than or equal to 0, or mu rather, sorry. Notice we don't need a lambda in this case because there's no equality constraint. And then we're going to have b transpose x. We have to be super careful with this minus here. Otherwise, the whole thing falls apart. Minus mu dot product with the positivity constraint. So it's a x minus c, right? Like that. Did I do that right? I think I did. Yeah. So normally in linear programming, like you can boil down a lot of what those classes are doing to a very simple thing, which is just swapping these two pieces. Notice that the Slater conditions here are very easy to check because, like, clearly you could choose a feasible point where mu is positive. You just choose it like 1, 1, 1, 1, 1. Yeah. So now let's solve the following: max over mu greater than or equal to 0, min over x, b transpose x minus mu transpose a x minus c. We can write this in a slightly different fashion, which is I'm going to factor out all the terms involving x. Okay? So this expression is the same as x dot product with b minus a transpose mu. That was supposed to be mu, but I got excited. All that plus mu transpose C. You see that? I just rearranged this expression. So let's use our new game theory brains to think about this problem. Let's say that this thing is non-zero. Right? So now the roles have flipped. Now we're trying to maximize this thing, which is min over x, and notice x is unconstrained. Yeah? So what happens if b minus a transpose mu? What happens if this is anything other than 0? What is going to be the minimum value? Well, I'm multiplying it by x, right? So I can get minus infinity. Then necessarily, we know that this thing is equal to 0. You see that? So that leads us to a dual linear program, which is as follows. Let's maximize over mu's. Notice all that's left if this is 0 is this term, right? Mu dot product with c, subject to mu greater than or equal to 0, and a transpose mu is equal to b. Okay, there you go. There's a dual linear program. Took 2 minutes. So incidentally, I can never remember the formulas for linear programming duals, and I just don't bother. I just write it as a Minimax problem and then swap the variables and regroup. I think even when you're doing specific examples, it's easier. Incidentally, this trick works for a very wide class of problems, including semi-definite programming and what are some other ones, like second-order cone programs and Lorenz cone programs and so on. They all follow the same pattern. Okay, so anyway, the good news. So now let's step back and you can ask an interesting question here, which is like, why did I bother doing all this? So let's say that A is in R m by n. Okay? What is the dimensionality of x? Well, notice that we've got an ax here, right? So then we know that x is in Rn, right? And what is the dimensionality of mu? Well, we've got an A transpose here, so we know that it's Rm. So here's a really nice thing, practically speaking. So there's some nice equivalence between these two problems, right? I can solve this one and then use complementary slackness to actually construct the solution to the primal. Well, it could be that A is extremely non-square, right? Like it could be that like this matrix has not very many constraints. In that case, it could be worthwhile to solve the dual problem because it's a lot smaller and then translate that into a primal solution. Yeah? And so a lot of algorithms, especially in the convex optimization universe, do precisely that. So like if you ever play with a fancy solver, you'll see that like for a little while it'll talk about optimizing the dual variable, and then sometimes it'll say, okay, now I'm switching to the primal problem. So like for instance, it'll like optimize mu for a while, and then maybe the numerical formula for getting x from mu is a little unstable, so then they like polish x for a few steps and then they stop. So that's what these algorithms look like. Isn't that cool? So like essentially convex programming and constrained programming more generally is this funny universe where there are like these little shadow problems that you can solve. Like for every minimization problem, there's another maximization problem that's equivalent or very close. And it's a really interesting and beautiful perspective. This is the beginning of like a giant rabbit's hole, like many math textbooks worth of stuff. This is just the beginning of it, but I think it's worth mentioning. And I think especially because people often lose the intuition. I think when you take like linear programming or OR classes, like this perspective is very clean. The only thing that's missing is justifying this swap here. And of course, that's an extremely non-trivial thing to do. Any questions about that little story? Very briefly, 2.5 lectures from now, we'll see a different version of duality, which is Fenchel duality. If you remind me, I'll try and call that out when it comes up. Chris got all excited. Yeah, we like Fenchel duals. Okay. All right, folks. So with that, as usual, please download your homeworks and run the starter code and read the problems. And that's all. I'm sorry, I got excited. So with that, have a fantastic weekend. And I'm going to go. In fact, see, I even set an alarm on my watch so that I wouldn't forget. Okay. And you sent a reminder. Fantastic. And I'm going to turn off the recording. Okay, guys. You are. See, he's the best.